Hey guys, back and continuing. I keep getting cut off. I apologize, and my handwriting is atrocious. I should retire and become a doctor, hey? Okay, so what I was saying there on top of page 19, they have a box that says frequency, wavelength, and C. Now, what they're talking about there is the talking about the wave equation that is applied for any type of wave: ocean wave, microwaves, light waves, heat waves, ultrasound waves. If I take the frequency, which is in hertz, and hertz is really telling us how many cycles per second, times wavelength, which is meters, I will get the product of meters per second, and we say that's V. Now we're going to change that to be a C because our velocity is constant at 1540 meters per second. Okay, so where does that come from? Well, that product is true. That holds for all types of waves. But for us, we call that C because it's constant. Again, where does this come from? It comes from the medium, and it's mainly from two things: stiffness and the density. Now, the stiffer something becomes as a material, the faster sound will travel through it. It is based on the engineering term bulk modulus. I think I've mentioned that before. A bulk modulus is on page 27, which talks about stress and strain and change in pressure over volume and things like that. It's really talking about, it's a measure of stiffness. Stiffness is also talking about the elasticity of it. If something is elastic, it's stretchy like a rubber band. We want the opposite, things that are not elastic or inelastic, and those things are going to be stiff. The stiffer they are, the faster things go through us. Now, we come up with a 1540 basically because we're taking soft tissue inside the body, and if you sort of blender it up so it's all similar, and we time or do a race of sound through it, we come up with 1540 as an average. But since that is the number we're going to always use, we say C equals lambda F is our wave equation. Okay? Now, they continue in Chapter 2 to talk a little more about how that happens and how propagation velocity is related to density and how it's related to modulus. We just want to know a couple general things. As the density of a material, all right, density is how much mass or stuff it has in the volume. As the density goes up, we typically see that the velocity of sound will go down. They're sort of proportional to that. As one goes up, it goes down. So they're inverse proportional. We also see as compressibility, meaning it cannot be squeezed or crushed, goes up. The ease of that goes down too. Okay? But we find that it is actually proportional. Velocity is proportional, will go up as the bulk modulus goes up. All right, and to say that in more public terms or layman's terms, we're talking about the stiffness. As the stiffness goes up, we see that the velocity of sound through there goes up also. All right, so this is the key. The stiffness one is sort of the dominant variable to make things really happen there. Now, as you go on to page 30, what you want to do is take a look at that table. It talks about the medium and relative propagation velocity. The key ones you want to memorize numerically are going to be air, which is somewhere around 331 meters per second, and water. Okay, water is a little over 1,400. And obviously soft tissue, which is us, which is 1540. Now, as you see, you go up into the solids, lead and brass, aluminum, steel, it gets into the thousands. Okay? We're going to look as bone being up there in the 3,000-4,000 range. So those two are really the ones we want, air and water. And then on page 31, you really want to memorize or look at that table. And we're going to pick that up in the next video.